Hello, welcome to part 1 of the gas turbine module. In this module, we'll cover a number of topics: how a gas turbine works, and the air standard Brayton cycle that models a gas turbine for analysis purpose, a complete manual solution, and how to use test calc to verify a manual solution. In your textbook, chapter 8 covers gas turbine, and you'll see the reference to various sections of different topics that we are covering. One important thing, you must be familiar with open steady device analysis in chapter 4. Especially, you got to go over how a compressor and a turbine works from chapter 4. Okay, let's begin with a screenshot of animation 8A simple gas turbine. In short, here is how a gas turbine works. Ambient air from outside is compressed by the compressor to a very high pressure, typically by a factor of 10 or 12. So if the pressure at the inlet is 100 kPa, typical atmospheric pressure, the pressure at the exit of the compressor will be, say, 1000 kPa. Of course, the temperature also increases because, as you know, in a adiabatic compression process, temperature increases with pressure. Now, in the combustion chamber, a little bit of fuel is injected, and as the fuel burns, the temperature rises sharply. So at state 3, at the turbine inlet, the temperature could be as high as 1000 kPa, 1000 Kelvin. This high pressure, high temperature gas then expands through the turbine, producing shaft power, WT, and part of which is fed back to run the compressor, WC. W.T is much higher than W.C. As a result, the difference, which is called the network, is what we are after. So, a simple explanation of how gas turbine works could be, oh, the turbine produces more work than compressor, that's why it works. But why does a turbine produce more work than the compressor? A very typical answer is that, well, the compressor raises the pressure from 100 kPa to 1000 kPa, and we are burning fuel in the combustion chamber, so that must be increasing the pressure at the turbine inlet. Nothing can be further from the truth. In a combustion chamber, when heat is added through the heat release of the combustion of fuel, the pressure doesn't increase. The misconception comes from the fact that whenever we think of what will happen to a gas if I increase the temperature, the instinctive answer is that pressure will increase. That's because in our mind, PV equals RT is kind of ingrained. If temperature increases, and if volume remains constant, then of course pressure will increase. In a closed chamber, volume doesn't change, therefore pressure increases. We just take it as a rule of thumb. In a combustion chamber, on the other hand, the volume of the gas, suppose think of a little bit of air, suddenly it gets hotter. Why should the pressure increase? It will simply expand. So you can understand that PV equals RT means P times V increases. So as a matter of fact, in a combustion chamber, as the air passes through, getting hotter and hotter, pressure doesn't increase at all because air is allowed to expand. As a matter of fact, you can show that because of friction, if anything, pressure slightly decreases. So at state 3, at the turbine inlet, the pressure is about 1000 kPa or slightly lower. At the turbine exhaust, what happens to the gas is it's thrown back into the atmosphere. So the pressure here at state 4 is again 100 kPa. So the turbine operates over the same pressure difference, 1000 kPa to 100 kPa, as the compressor operates, 100 kPa to 1000 kPa. So a question can be raised, shouldn't the turbine work be exactly equal to the compressor work? Well, The second explanation is, well, the gas is hotter at state 3, so turbine should produce more work. But just because gas is hotter, why should turbine produce more work? And that explanation goes to, if you recall from our chapter 4 review, that the work in any internally reversible device is given by integral VdP between the inlet and exit. The work is proportional to integral VdP, which is, in a PV diagram, the area which I am hatching. So for a compressor, this will be the area, whereas for the turbine, the area will be, let me pick a different color. The turbine work, see, it goes from 3 to 4, so the turbine work must be, this is the shaded area. So as you can see, the turbine work is much higher than the compressor work because the specific volume handled by the turbine is much higher than the specific volume handled by the compressor. So the hotter the gas is, the higher is specific volume, and therefore turbine will produce a lot more work than the compressor will consume. So that's the bottom line. So why does a gas turbine work? In a single sentence, a turbine and compressor, they operate under the same pressure difference. However, because the specific volume inside the turbine is much higher, it produces a lot more work than what the compressor requires, producing net work. Okay, now let's see how we can model this. This is not a cycle, this is the real gas turbine. How can we simplify this so that we can analyze? Well, first thing, a compressor, we'll assume it to be ideal. So let's go to so when we simplify things, turn it into a cycle, that's called the Brayton cycle. In Brayton cycle, of course, the compressor is modeled as an isentropic compressor. No heat transfer and no friction makes a compressor isentropic. So from 1, which is the atmospheric state, we go to 2. So if these are constant pressure lines in the TS diagram. So this could be pressure equals 100 kPa, and this could be pressure equals 1000 kPa. So at state 2, we have a much higher pressure. Entropy doesn't change between 1 and 2. And look at what we have done to the combustion chamber. Because very little bit of fuel is added to the for the heat release necessary, the mass flow rate m dot 2 and m dot 3 are almost equal. The amount of fuel mass that is injected is almost negligible. So this is one assumption in Brayton cycle, that the same mass that exists the compressor is what enters the turbine. There is no change in mass flow rate. Second, instead of adding fuel, the complexity is avoided by saying, you know what, we are adding heat here, Q dot in. So this is equivalent. Suppose we are putting a little bit of fuel, multiply that by the heating value. So that translates to how much heat is added into the combustion chamber replaced by this heat exchanger. And furthermore, as I said, the pressure doesn't increase in a combustion chamber. It actually decreases slightly because of friction, but in Brayton cycle, we assume that the pressure doesn't change. So the heat addition Q dot in is assumed to take place at constant pressure. See, 2 to 3 is a constant pressure line, and so heat addition takes place at a constant pressure. 3 to 4 is an isentropic turbine. Again, you're familiar with the turbine, how it operates and how to analyze a turbine. It's just the inverse of the compressor. And in case of a turbine, again, we go from state 3, which is the combustor exit temperature, which is at the maximum temperature of the cycle. And at state 4, again, the pressure is atmospheric because in reality, the gas is thrown away into the atmosphere. But to complete the cycle, from state 4, we put another heat exchanger and take heat out and bring back the gas back to state 1. And the gas we are talking about is pure air because in this cycle, same air is circulating from device to device. So look at how simple this cycle has become. From 1 to 2, we have a compressor, isentropic compression. From 2 to 3, we have constant pressure heat addition. 3 to 4, we have isentropic expansion producing shaft work. And from 4 to 1, we have again constant pressure heat rejection. So in short, that is what constitutes a Brayton cycle, which models a real-life gas turbine. Okay, we'll now go one device at a time, analyze each device, and our goal is to set up the equation so that we can solve the gas turbine problem. So here, let's analyze the compressor. The energy equation, as you recall, m dot J1 minus m dot J2 Now, let's apply this equation to this particular compressor. It's an ideal compressor. First of all, the steady state. Because of steady state assumption, the unsteady term goes to 0. Typically in a compressor, heat transfer is 0. Compressor is mostly adiabatic. An ideal compressor is always adiabatic. So the equation simplifies to m dot J1 minus J2 minus W dot external. Now recall that W dot external has sign associated with it. It's an algebraic quantity. For a compressor, we know intuitively that W dot external must be negative. But what is W dot C? W dot C is a positive, is a magnitude. The compressor work. Compressor work means just a positive number. So if we say yes, the compressor power is 50 kilowatt, that means 50 kilowatt of work is necessary, is going into the compressor. So we don't go to Home Depot and say, give us a negative 5 kilowatt pump. If you want to buy a pump, you say, give me a 5 kilowatt pump. It's understood that 5 kilowatt is consumed by the pump. Similarly, when you say W dot C is a positive number. W dot T, W dot C, these are all positive numbers. So to substitute W dot C into this energy equation, we must put negative W dot C. And notice, because of that, if we get an expression for the compressor work, negative made it plus, so we switch side here, so it will become m dot J2 minus J1. And if we neglect kinetic energy, recall that what is J? J equals H plus KE plus PE. So if we neglect kinetic energy and potential energy, then we get m dot H2 minus H1. So how do we figure out enthalpy difference between two states for an ideal gas or a perfect gas? Again, we are going to use the PG model, the perfect gas model, all the time whenever we encounter gas, because it's the simplest model to use. So how do you figure out H2 minus H1? You probably already know it, but just to show you where to go, for any formula, we'll make a habit of going to a handout that you should print out. Go to the tables module. Table J is where you'll find our formula sheet, and in there you'll find governing equation for mass, energy, and entropy for different kind of systems. And this is where the last page is about all the equations you need to find properties. So we are applying the PG model, and in PG model, the formula for delta H, as you can see, is given by Cp times delta T. And I'm pretty sure you probably have memorized that by now. So the formula for compressor work will be m dot Cp times T2 minus T1. Of course, we understand that T2 is higher than T1 because in a TS diagram, if we draw the compressor on a TS diagram, here is a state 1 and entropy remains constant. This will be state 2. We can see the temperature must be higher at T2. So you notice that T2 minus T1 is of course greater than 0. So therefore W dot C is a positive number. So a compressor work that we'll find would be m dot Cp T2 minus T1 is almost an intuitive formula. So another way to understand the formula physically is that the compressor work is the flow energy at the exit minus the flow energy at the inlet. After all, the energy that goes in work, the compressor work we put into the compressor, it raises the energy that goes into the compressor, and the energy that comes out, the difference must be the compressor work. So it's a very intuitive formula, but here we have developed it from scratch. Let's now go to the next. So we are modeling here a constant pressure heat addition. Let's do it on a TS diagram first, how it will look. So we have already analyzed the compressor, and from 2 to 3 is our constant pressure heat addition, if you recall. So if we call the heat addition Q dot in, we want to find an expression for Q dot in. Again, starting from the energy equation for an open steady device, m dot, instead of J, let me just directly use H. Instead of J, we are using H because kinetic and potential energy are mostly negligible. Again, steady state, d dt goes to 0. There is no external work. We don't see any shaft or electrical work transfer or boundary work in a heat exchanger. So the formula simplifies to m dot H2 minus H3, and Q dot, what should we substitute for Q dot? Q dot in is a positive number, and we know in this case heat is going in, so we don't need any negative sign. Q dot in is Q dot. It's a positive number, and that produces the desired formula for heat transfer, m dot H3 minus H2. And notice how it makes sense. What is Q dot in? The energy that is going in. Again, you can see that the energy that goes in is the difference between the energy, the flow energy coming out minus the flow energy that goes in. What is the flow energy that goes in? M dot times J2, and J being almost equals to H, it is M dot times H2. So therefore, the difference between these two flow energy must be Q dot in. So we got, again, applying the ideal gas, the perfect gas equation, it will be T3 minus T2. We also know that it is also, in the TS diagram, this must be exactly equal to this area. Okay, now let's move on to the turbine, our next device. As we have made a habit of, we'll draw the TS diagram for the device as we analyze it. Again, 1 to 2 is the compressor, 2 to 3 is the constant pressure heat addition in the heat exchanger, and 3 to 4 will be our turbine. The energy equation is simple. just like the compressor. Steady state, adiabatic, and W dot external is W dot T, because W dot T is a positive number, and we know the turbine work is positive, it's coming out of the turbine. So work out is positive, so therefore it gives us a formula for the turbine work to be m dot h3 minus h4 equals m dot cp t3 minus t4. So notice that T3 is higher than T4. Again, what is turbine work? The energy that is transported by the flow energy that is going into the turbine, and some of it is coming out. So the energy that is as turbine work, so the energy that leaves with the flow will be less. So the difference between the energy that enters minus the energy that leaves is the turbine work. So this formula makes total sense. One thing I haven't shown is that in an ideal turbine or an ideal compressor, the entropy remains constant. And let me just do it for turbine, and for compressor you can use similar logic. The entropy equation for the turbine can be written as m dot S3, m dot S4, q dot by TB, s dot gen, right? In other words, the entropy equation means the rate at which the entropy in the system is changing is given by the rate at which entropy is carried in by the flow minus the rate at which entropy is carried out by the flow, plus the rate at which entropy may enter through heat and entropy may be that is generated because of friction inside the turbine. For this particular system, steady state, no heat transfer, and if it's an ideal turbine, no friction. So therefore, you can see S3 equals S4, which is called an isentropic condition, isentropic turbine. Just like the compressor is isentropic, the turbine is isentropic. And what are the conditions for a turbine being isentropic? It's at steady state, no heat transfer, and no friction. Well, finally, let's complete the cycle by analyzing the heat exchanger where heat is rejected. Oops. So we'll again do the TS diagram like we have been doing. State 1, isentropic compression, constant pressure heat addition, isentropic expansion, and finally constant pressure heat rejection 4-1. The energy equation, m dot h4 is the inlet, h1 is the exit. This is the standard energy equation applied to the system where flow goes in at 4 and comes out at 1. Steady state, no external work. So if we customize this equation for this system, what will happen to q dot? We know heat is going out, and q dot out is a positive number, but this q dot has sign in it. So you know heat goes out means win hip. There's the sign convention if you recall. So it'll be minus q dot out because q dot is negative. Q dot out therefore equals m dot h4 minus h1, which is m dot Cp T4 minus T1. Okay, now that we have analyzed each device, let's go over the ideal Brayton cycle animation one more time. Notice that air in the compressor is compressed from state 1 to 2. From 2 to 3, the constant pressure heat addition takes place in the heat exchanger. And the hot air is then expands to the turbine, isentropic expansion from 3 to 4. And finally, from 4 to 1, we have another heat exchanger where heat is lost at constant pressure. Q dot out takes place here, and we get back to state 1, completing the cycle. The net area inside the TS diagram or the PV diagram represents the net work or net heat transfer, which are equal, and the thermal efficiency is given by the net work divided by Q dot in and given by this following formula. Again, as you go over the animation, you'll find the formulas that we have derived: compressor work, heat exchanger 1, Q dot in, turbine power W dot T, and heat exchanger 2, where Q dot out takes place. This is a good time to take a little break and come back with the solution of a problem I've separated into a separate video. So please go over the example problem 811 in the separate video before you move on to module 2 of gas turbine.